Welcome all of you for today's session. So week 3 session for the Advanced Research Trends in Smart Grid Technologies course. So I'm Gagan Meena and I'm doing PhD at IIT Bombay in Electrical Engineering Department. So I'm TA for the live session for this course. So this will be the basic flow for today's live session. First of all, we will discuss a brief overview of week 3 and then we will discuss some questions regarding the week 3. And while discussing the question, we will also go through some important concepts related to the topics mentioned in the questions. And then we'll have some doubts. If you have some doubts, we can go through the doubts. So let me first remind you that deadline for assignment 2 is February 22nd and for assignment 5 is March 1. And the live recording sessions will be available on the YouTube channel. You can also watch the recorded lectures. So let us quickly go through week 3 overview. So before that, let me ask you if you have, do you have any doubts in the previous 2 weeks material, week 1 and week 2 material, or assignments of week 1 and week 2? Are there any doubts? Am I audible? Saurabh, am I audible?
Yes, sir.
So, do you have any doubts in week 1 and week 2 material?
Not now, sir.
Okay, okay then. Okay, then let us continue with the week 3 material. So, we'll quickly go through week 3 material. I think this should be week 3. Sorry for that. So, in week 3, we discussed introduction to energy storage systems. Then we discussed different types of energy storage systems. And then how to model energy storage systems. Then we also discussed how to optimally size and site energy storage for a distribution system. And then finally, battery management system was discussed, which is an essential part of any storage system or battery storage system. So in introduction of energy storage, we studied the purpose of energy storage. So can you tell me any one reason why are we going for energy storage? What is the need of energy storage? Any of you? Any one need that you can remember from lectures? Energy storage can provide several benefits. So one of the need, increasing or growing need of energy storage is in power system is uncertainty or variability in the renewable energy resources. Because we want to make our power system green. We want to move away from conventional system and use renewables. But they are intermittent and variable. So to mitigate those challenges, one storage provides a very good solution. So one of the reasons for using storage is that. And we also discuss history of energy storage, how it started, different types of energy storage, when did they come into picture. And then we discuss classification of energy storage. So there are different type of energy storage like thermal storage. We have chemical storage, electrochemical storage, and we have mechanical storages like pump storage, which is most common and we can say one of the most widely used. And then flywheel also. So the need of ESS in power grid, we can say we can. So these are the applications of energy storage. So first one is system operation. Investment. Then in system operation, we have these different types of applications like frequency regulation, flexible ramping, black start. Some of these is flexible ramping. We will discuss in further slides also. So frequency regulation, let's start. We have also discussed in uh, first week. I will again repeat it. So let's start is some when the grid is and all the components of power system are shut down. Then to again start the system, we need these services because these generators. Suppose let us take example of this thermal generator. So thermal generator, they need several auxiliary supplies. They have auxiliary components which are required to enable the thermal generator to synchronize to the grid, to feed into the grid. So those auxiliary equipments they require power. But when the grid is down, then either we have to use diesel generator to provide those auxiliary components power. Otherwise, storage is one of the good option because it can quickly do so. So that is black start service which storage can provide. Then there are frequency regulation services. This is one of the ancillary services, and there can be three types of frequency regulation: primary, secondary, and tertiary, depending upon how much is the frequency deviation. For minor deviation, we will go for the primary regulation. So if frequency goes below or above the nominal frequency, which is 50 hertz for our case, then storage can charge or discharge to maintain that frequency level. So in that also storage can do that quickly. So different type of storages are there. For example, flywheel and battery storages or these supercapacitor. These are very quick. They have high power density and they can quickly discharge. So flywheel are being used for providing these frequency regulation services. Also, lithium-ion battery storage systems are also being used for providing these frequency regulation services. For example, in US, we have this Moss Landing, a very big 300 megawatt energy storage system, which is providing this frequency regulation services. Then we have these investment deferral services. So by using storage, we can reduce transmission and distribution congestion. As a result, we can reduce requirement of new lines. Why do we need new lines? Because our existing lines are already congested, so we need new lines if a new generation is coming up. But if we are able to reduce that congestion, we can reduce the requirement of new lines. Storage can help do that by providing counter flow, or it can also suppose Suppose this is a line. So here we have a load, and from here we are feeding some power. And this line is, suppose this line is congested. The power flowing is more than its maximum power. Then what we can do, we can have a storage here. So this storage can provide power to the load. So that this F will be reduced by, suppose this storage is providing PL power. Let's call it P and this is load PL. So this will be reduced by P amount. So we can maintain it to its maximum or even below that value. And storage can discharge to provide power to this load. So by doing this, we can reduce the congestion on the line. Another like, same thing can also be done by having two batteries, two storages on these two buses. So in this case, what will happen? We want to send power from here to this load. So in this case, what will happen? This storage is S1 and this is S2. So this storage S1 will be charged and S2 will be discharged simultaneously. Suppose this extra amount is F plus delta F. So delta F, this will be charged, and this S2 will discharge delta F, so that this F is maintained at F max, and this load is getting its full power, full demand. So both these configuration can be used. So in this way, we can avoid investment in new transmission line by reducing the congestion. Okay, so next is this PV and wind generators. So storage can help in reducing renewable curtailment and also in capacity firming. So can anyone tell what is capacity firming? Any of you who has heard this term before, this capacity firming?
The capacity which generator generate the power is called capacity firming, I think so.
Okay, I will correct your statement a little bit. So what you are saying is correct if those generators are the conventional generators. If conventional generators are there, even for them also, if we remove the outage rates, they have their forced outage and they have scheduled outages. These are planned, so we don't consider them. We already know. But these are forced outages. If we remove them, then the capacity what these conventional generators are generating, they will be their firm capacity. Because we are sure we will get that much capacity. But this is not the case with the renewables because they are weather dependent. They are temperature, if the temperature changes or there is a sudden cloud cover, then the output of solar PV will change. Or if suddenly wind stops blowing or there is a very wind speed is very large, very then also the PV wind generator may not produce power. So in that case, we will not be able to provide the required power which solar and wind were supposed to provide. So in that case, if we have a storage, let me remove this.
Hi.
Yes, yes.
Actually, Padhy sir and Premalata ma'am couldn't join this meet.
Okay. Yes. Oh,
Hello.
ma'am. Yes, ma'am was ma'am going to attend this?
Hello.
Yes, yes. I can hear you. Can you repeat?
Yeah, I could not hear you. Ma'am has not joined the meeting. Ma'am and sir, Padhy sir and Premalata ma'am.
Okay. Are they going to join? No problem. Uh, so, suppose this is a PV generator, right? And suppose it was scheduled to provide this P amount of power, P megawatts, but due to some cloud cover, there was a reduction in generation from here. This was P minus some delta P. Okay, then if we have a storage here, then what can happen? This storage can provide this delta P amount so that we can still provide P megawatt. So storage here is helping in firming the output of PV. Similarly with wind also we can do so. So all these generators are scheduled to provide some required amount of power on a day ahead basis. They know that tomorrow based upon forecast they will tell that they will provide some P megawatt of power. But if they deviate, then they have to provide penalties. They are liable to be penalized. But so if we have a storage, then we can avoid that case and we can still provide that required power. Similarly, if this renewable curtailment, what if there is seasons like spring season, we have excess amount of PV generation because the demand is lower in spring season. So in those months, what happens? The PV generation is more than the required demand. So this excess is usually wasted. So we have to curtail it. Sometimes it is curtailed. But if storage was there, then this excess PV generation can be used to charge the storage, which can then be used to discharge again when required. Suppose in the night time when PV is not there. Then last one is the mini grids. So in mini grids, storage can help in reducing reliance on the diesel generators. So, so in isolated grids or mini grids, if there is no generation, then diesel generators are used right now to continue the power supply. But if we have storage, then we can avoid those diesel generators or at least reduce the requirement of diesel generators. So both the emissions, carbon emissions can be reduced as well as the cost. Diesel generators are very costly. This is smart grid session only. Yes, yes, this is smart grid only. So we are discussing the week 3 of smart grid course, right?
Yeah. Yeah. I also know this is week 3 battery management systems.
Yes, yes, yes.
Yeah. Actually, I have one doubt in week 4 regarding the problems. I
Uh,
couldn't find the formula to solve the or two problems, that angle calculating and sampling the cycle frequency. I thought this is problem solving session. I could expect
yeah,
that
it is
problem solving.
actually it is a 2-hour session. So We thought first we'll go through a brief overview and then we will take your doubts.
Yeah.
Because usually what
Okay, I
happens,
can. I
yes.
Yeah, yeah. You can continue.
Okay. So then we discuss the case studies of utility scale battery deployments. So let us move to the second. Then we discuss these battery modeling methods. So there are these three types of modeling methods like electrochemical equivalent circuits and empirical. So we focus more on these equivalent circuits, and then finally we discuss this battery management system. The role of battery management system in battery energy storage system is immense. It is very important part, an essential part of an battery energy storage system. Where it does so many things. It measures current, voltage, temperature, does the cell balancing, and then estimate the state of charge and state of health of the battery. Also helps in thermal management. Then protection against short circuit overload and deep discharge, and also help the storage communicate with external devices or with cloud, so it can share data and display status. So can anyone tell why do we need to estimate the state of charge and state of health? What's the requirement of measuring these two? Any one of you? The state of charge will tell us how much available capacity is there in the battery at present with respect to its maximum capacity. Because we want to prevent deep discharge as well as overcharge. But to know that battery is under a deep discharge state or under overcharge state, we need to know this state of charge. Then only we can prevent those. And also, suppose automobile is there, we are driving, then we need to know how far can we go, and that depends on the state of charge. So these things are very important. Similarly, state of health. It tells us about battery degradation, its life, how much is number of cycles more charging, discharging the battery can does. Also, thermal management is very important. We have also seen several cases of vehicles catching fire. So, if thermal management is not proper, not adequate, then such events can occur. So, we have to prevent that overheating of batteries. For that, also battery management system is there. Then we have let us see some advancement in this battery management system. So these are some new techniques which are being deployed in battery management system. First one is this wireless battery management system, and then we have this smart BMS. So wireless battery management system. What happens that one battery has several packs, different packs, and each pack has a small its own BMS. And there is one cell. One this is cell, so we can say this is module, and these are pack. So each pack hits BMS, and then they will communicate wirelessly to this BMS. So earlier it used to be wired, but now it can also be done wirelessly. So it increases the efficiency because we are reducing wires. And then this smart BMS are there which can help us visualize all the battery statistics. These two can be combined together. So we can have smart BMS inside this also. So then we have this is a new technology, AI powered digital twin cloud BMS. So benefit of cloud is that we can do computations on cloud using the storage available in the cloud. It's memory storage. So we can use advanced algorithms which require good amount of computations, and we can do that computation over the cloud and then send the data back to the storage. So digital twin is this is also an advanced technology, a new technology. So here this is you can say, it's a virtual model of the same physical object. In some movies you would have seen that doctors they are using some 3D models to simulate to perform operation on that 3D model, because that 3D model of that suppose heart cardiologist is there and he wants to operate on a patient, but before operating on the real patient he wants to do the same surgery on this 3D model. So that 3D model will simulate the heart of that patient exactly as that patient's heart is. So the doctor will perform that entire operation on that 3D model. So that is a digital twin technology. Similarly, there is one company GE. So they produce these wind turbines, and they have several wind turbines they have connected to these digital twins. So this digital twin will have this virtual model of real wind turbines. So these wind turbines will have some sensors which will provide data to this virtual model of wind turbine, which will do some analysis and again give data to control this wind turbine. The same can be also done for the storages. Then one question is, why are we moving to battery energy storage systems when we have we know that most of the around 99, even more than 99% of storages are right now by installed capacity are pumped hydro storage. But we are moving towards battery. So what is the reason? So this is also in India also most of the storage that we have right now is in the form of pumped hydro storage. We have very small scale battery storage projects right now. So one that 10 megawatt storage by Tata Power and Distribution Company in Delhi. So there are several other PSUs like NTPC, ONGC. They have installed some small storages, but most of them is still pumped hydro. But pumped hydro is geography specific. We cannot have pumped hydro everywhere. It is restricted to a particular geography, and also it is based upon the available potential of hydropower. We have a limited potential, but our requirement is huge. Considering our goal of achieving 500 gigawatt of renewable energy by 2030, the requirement of energy storage is going to be huge, and that cannot be met only by pumped hydro storage. And battery is one of the good options, and because there are several projects are running in world throughout the world. Now we have around the maximum. Uh, this is 409 megawatt in this Manate that we also saw in the lecture. Also, then there are another 400 megawatt and 1600 megawatt hour battery storage in Australia also. So now we are moving more towards battery, and it is also more flexible and it is relocable. You can place it anywhere. Only condition is space requirement. So, and generally we have these storages near to renewable plants where we already have spaces, so we don't have much space restriction also. So battery has several advantages. Then one recent development in battery, one we see that all the automobiles right now they have around a range of maximum 500 kilometers. EVs, if you talk about EVs, on single charge they can provide only this much range. But this new type of battery, they call it Gemini battery. They invent our next energy is their inventor. They claim the range is around 965 kilometers. So they use this uh, two batteries, LFP and lithium manganese oxide. Sorry. So first to 40 kilometer they will use this LFP battery. Then for next remaining journey, this another chemistry is used to achieve this range. Now we'll take some questions based upon week 3 material. So first question is, which of the following is not an electrochemical energy storage? So which one is the correct option? Anyone? Can you tell? Which one of these is not an electrochemical energy storage? Anyone? So these three are electrochemical, and this is a chemical. However, although yes, anyone? Jay, do you want to say something?
No, no. Synthetic fuel. Can you explain a composition of synthetic fuel?
Composition, I don't exactly remember. But
Okay.
it is one of the gases, similar to syngas.
Okay. Right, right. Thank you.
So all these three are electrochemical. However, these three are different technologies. This is flow batteries. This is high temperature battery. So right now, what we have in market, so most of the storages that are widely used are one is lithium ion, which can provide the discharge duration around 2 to 4 hours at present. Then we have this sodium sulfur, which can provide around 6 to 8 hours of discharge duration. And then this VRF batteries are also, vanadium redox flow batteries are also being used, but not much. They are being used in hybrid with lithium ion. We will see what is the advantage of using them in hybrid. So let us move to the next question. So this is the next question. We have, which of these is not a system operation service? So we have also discussed this. We recently, in I think initial slides, we discussed the three system operation services. So which one is not a system operation service? So we discussed, right, that system, these three are the system operation services. And this transmission and distribution investment deferral is it's a planning problem. So these three are the operation services. This is the correct option. So in the system operation services, we discussed these three. One was frequency regulation, then there's flexible ramping, and then leg start services. So you can see here this region and this region. So this is called duck curve, and this is from this California ISO. So this this trough in this curve is because of the renewable, because solar generation is more during this time. So the net demand is less. And you can see here from 2012 to 2020 it's decreasing because of increasing renewable penetration. So suddenly you can see from here to here, from 6 to around 8 p.m. So we need to jump from around 13 gigawatts to 26 gigawatts. So that is a huge jump. So this is the ramping requirement that we have to meet. So those thermal generators, they have to quickly do that. If storage is there, we can storage are more quick. And gradually, as the renewable is decreasing, the other generators have to pick up to meet the load. So these are the requirements of a generator which can provide a quick ramp up, ramp down, and for a long duration of up and down. And quickly it can change from plus to minus ramping requirement. Suppose it was generating, then suddenly it has to reduce its generation. So that battery can do that. Thermal may not be able to do that quickly. So within few minutes, it may not be able to do that. But battery can do that. So these are the requirements for an ideal generator which can provide this ramping. So it should have a quick start and it can do frequent cycling. So it can be on, then it can be off, then it can go negative also, off, on. So it has to quickly do this. So energy storage can provide this type of services, especially these flywheels. They are very quick. Then let us move to the next question. So next question is this. Out of these, what are the two battery aging phenomena? So we have discussed in the lectures that there are two kind of battery degradation processes. So what are these two processes? Do you remember? Anyone? So these are the two processes. One is the yes. Anyone wants to say something?
Should be a B and C. Calendar as well as inherent also. Inherent properties also changes na, with time.
That is correct. Inherent property also changes, but we have specific names for these two processes. Your calendar is correct, and this calendar is also due to this inherent. These are due to these inherent processes. So this option, we can say this is a only one process. The other process is this cyclic aging. So these are the two processes. This calendar aging is because of these inherent phenomena, such as this. So over a time, batteries inherently it will go undergo degradation because of increase in battery resistance or capacity fading. Then another process is the cyclic aging, which is due to this operation. As the number of operation of battery increases, the number of cycle of charging discharging increases. That results to another kind of degradation, which is called cyclic degradation, cyclic aging, and it depends upon this depth of discharge, discharge rate, the limits on SOC, and the temperature also. So we can see this graph. So this graph shows the degradation of battery over time. So this is the life of battery, and this is the depth of discharge, and also these different curves show the different charging rate. So from this curve we can say if we discharge battery more, then we'll be able to use battery only for lesser number of cycles. Furthermore, for the same depth of discharge, if the discharge rate increases, then also the life of battery reduces. Because we see this curve corresponds to 5C, and this corresponds to 0.25C. So C is the C rate, we call it C rate of the battery. It measures how fast it is discharging or charging. So if there is a 1C battery, that means it can discharge completely in 1 hour at the rated capacity. So if it discharges at its rated capacity, then it will discharge in 1 hour completely. So 0.25C. So how much time the 0.25C battery will take to discharge? So suppose a battery discharge at 0.25C, how much time will it take to discharge completely? If 1C is taking 1 hour, you can use unity method, right? How much time will it take? Can you tell? 1C is taking 1 hour. 2C will take 2 hour. 2 hour.
5 hours.
Which one? 0.25. See?
0.25C, 4 hours.
Correct. It will take 4 hours, and 2C will take
C will take
C will
half
take
hour.
C will
Half
take
hour to C.
yes, 2C will take half hours. So
Yes.
5C will take 0.2 hours.
Yes.
So suppose if we have a 30 kilowatt hour battery in a car, and we have a DC 300 kilowatt charger, and the C rate is 6C. So how much time will it take to charge completely? So it, it will take 1 by 6 hours, so 10 minutes. So that is why we are going for fast chargers, fast DC chargers. Why only DC and why not AC? Why are we not going for AC fast chargers? We already have AC supplies. Why to convert it into DC, then charge the battery? Why not directly take 300 kilowatt AC input and then charge the battery? Any guess?
DC side voltage reduces, na current increases.
Okay, so then
Ultimately, power requirement remains same.
yes, but
Yeah.
that is not the reason. Uh,
Okay.
reason is a very important reason. It is limit based upon it is due to limitation of the vehicle itself, because
Okay.
we have on vehicle we have a onboard charger.
Yes.
When we connect it to our home supply, right? So we have this AC supply at homes. It will convert it. Suppose we are using that 15 ampere socket. So it will convert it into DC and then the battery will be charged. But this charger, onboard charger has limitation. It has some rating. So it's maybe 3.3 kilowatt or 7.2 kilowatt. It depends on the rating. Because now one may say that we can increase the size of this converter, but that will add to cost as well as to the size of the converter, and it will add to the weight of the car. We don't want that because we want car to be cheaper as well as light. So we cannot have bulky converters on board. That is why we are going for off board converters. So if these are DC, we can directly charge the battery. We need not go through this stage, AC to DC conversion. We can directly charge this. Okay. So this is we just talk about this. So the C rate is a measure of rate at which the battery is discharged or charged relative to its maximum capacity. Same that 1C rate means that it will discharge entirely in 1 hour. It depends upon the battery chemistry and ambient temperature. So these are some chemistry. So these 1C are these lithium LFP, LTO. So LTO provides this It can provide up to, this should be 6C. It can provide up to 6C. So it can charge within 10 minutes. So these DC fast charger, or this, the cars also should have this. The battery inside the car should have this chemistry. Even though we have a fast charger outside, if our battery doesn't support this much, we cannot quickly charge. It will still take time. Otherwise, if we charge this chemistry at C6C, then we have already seen that what will happen. This curve. So, battery life will reduce. If a battery is designed for 6C, that we can charge or discharge at 6C. So for that we need this chemistry. We will not discharge at this, because but we will charge at 6C. We want to quickly charge. We have to discharge it slowly so that we can cover the entire range. So we have already discussed this one. Now the next question is, oh, this is already done. Which of this is not a firm generation resource? So we discussed, while we were discussing these different services which battery can provide, what is a firm? What do you mean by firming the capacity? So which of these following is not a firm generation resource? Thermal, nuclear, hydro, or solar PV? Which is the correct option? What do you think? You can add wind also. So which of these can provide firm generation? Anyone? We just discussed, right, that this thermal, nuclear, and hydro conventional generators, they can provide firm generation. But since the solar and wind, they depend upon their input itself, which is the solar irradiance or the wind speed, and they are random variables. They change. We don't have control over these. But we can control this input to this thermal, nuclear, and hydro. And thus we can provide the fixed output. But here, it's not in our control. So they are not firm. But storage, by using storage, we can do that. We can farm their output. So let us move to the next question. Next question is, which of the following can help mitigate seasonal imbalances in load and generation? Let us first discuss what. Let me tell you. Do you know about seasonal imbalance in load generation? What do you mean by seasonal imbalances? It is similar to what we have discussed. Any guess you would like to make? What is the seasonal imbalance? Anyone?
Seasonal increase in demand, sudden peak demand. Better to by pumped hydro will be the better.
Right.
Seasonal imbalance, those demands come occasionally, not always. Sudden change in demand. Suppose now the hot season has started,
Yes.
demand has
Correct.
These are the conditions.
That is correct. So you are saying about demand. So we can also, if we only had, if we had only these conventional generators, then you are correct. Then the imbalance is mainly due to this demand side, because in, especially in summer, we have huge demand in comparison to other seasons, spring or autumn. In summer and winters, we have more demand because of this cooling and heating requirements. But because of these generators, new type of generators, these renewable generators, they also add up to this situation. So what happens? Suppose this is, if we see, we can say this is winter, you can say this spring, autumn, and this is summer. Let us say demand follows this one. So we can see these two peaks, and these peaks are coming at different times. So we have excess generation at a different time and excess demand at different times. So if somehow we are able to store the excess generation here, this excess generation, especially when there is a high renewable penetration, so this excess generation from PV and wind, if we are able to store it in some storage, then what we can discharge it during these two peaks. When generation is lesser and demand is more. So this is called seasonal imbalance. And for this type of imbalance, we need storage which can discharge over a long time of period, which can provide long discharge. So lithium ion right now, what we have in market, they can only provide a discharge duration of around 2 to 4 hours only. So they can help in mitigating this load generation balance within a day. Within a day. Suppose if a system has very high PV and wind penetration, thermals are very less, then in within day during nights we will need this storage. So, so lithium ion and battery, other type of batteries can provide this service during day, within one day. So between day to night. But more than that, the batteries will not be able to provide. So we'll have to go for some other. So these two, compressed air and pumped hydro, both are mechanical energy storages. They can provide longer discharge durations. Right now that we have, for them also we have around, we can say highest is around 28 hours. If it discharges, it's not exactly, I don't remember, but around 25 to 28 hours. And three gorges dam is there. One more dam is there. Sorry, three gorges is not pumped hydro. There are some dams which can provide this much of discharge duration. But if you want more than that, suppose there is prolonged low renewable output, especially during, this happens during winters. If there is extreme weather phenomena, extreme winters, then both solar and wind will be less, output will be less. And if we have no thermal, then even this will be discharged completely. So this will also not be able to provide. So the option that is right now in research, which is being thought of as for providing this seasonal storage for mitigating this seasonal imbalance is chemical based energy resources, and mostly we are thinking about this hydrogen. So here the correct option is hydrogen. So Jay, you told correct. This pumped hydro can also provide a long discharge duration, but it also has certain limitation. And studies have shown that this hydrogen, and other thing is also when we think about a resource for any option, we also think in terms of economics. So when we want a long discharge duration, then we want the energy cost. The cost of providing that energy has to be very low. And among these four, hydrogen has least energy cost, which is favorable for it to be used as a seasonal storage.
It may be for future, but for present
Yeah,
conditions,
that is true.
hydrogen is costly. Yeah,
Yeah.
maybe
No,
for
but
future.
hydrogen is costly, but still its energy cost is still very less in comparison to these. But right now we are not using hydrogen because we don't have even use case, no? Because right now this renewable penetration is not that much. We are able to. We
Yeah.
have this thermal is still around 60% is still thermal, and we are using it. And government is not planning to. They are planning to maintain a status quo with respect to thermals.
Hydrogen and lithium ion both are not economically viable for India. I can say right now, best is for pump hydro. That was
Yes,
my thinking.
like
Present conditions.
that is.
Yeah,
I will give you one example of Karnataka state.
yeah.
So in Karnataka, what is happening is sometimes, as per their data, during some hours, it is even generating more renewable power than the demand within the Karnataka state. So they are exporting it to other states.
They
And
have big parks, na?
yes,
The
correct. That is why.
big
And
parks.
mm, and other times when the generation is lower than demand, they are using their hydro. They have pumped hydro and other hydros also, that normal hydro reservoirs. They are using it for balancing generation and demand mismatch. So right now you are correct. That is absolutely correct. Pumped hydro is the only economical option right now that we have, and lithium ion is also very costly right now. But we are planning to shift as per the CEA report. So we have to achieve this 500 gigawatt by 2030. So as per that, they have made one transmission expansion plan. In that, uh, they have given place to this lithium ion. Around 60 to 90 gigawatt of this lithium ion will battery energy storage will be required for that amount of renewable penetration. This problem will increase when renewable penetration increases because pumped hydros can be constructed only at few places, and that too constructing pumped hydro requires it has a long gestation period. It will take years, but within 6 months or maybe within 1 to 1.5 years, battery plant will be ready.
Hope so. We have got lithium now.
Yes, we are moving to lithium, although it is not economical. In other countries also they are moving to lithium. There are big plants, 400 megawatt. We are also planning in. We have one planned around 13 gigawatt hour of energy storage in Leh and Ladakh. We have planned that, so we will see that in coming years because they in Leh Ladakh we are going to have 13 gigawatt of solar and wind farm. To extract that we need this much, and they have come up with a study that if we use energy storage we can reduce the transmission requirement by half. So they will use it. So this is approved, this project has been approved and they are going to construct it. So in
Okay.
long, yes, sorry. So in long run, we are hoping that hydrogen is going to become economical, and that is why government is also planning with has announced this national green hydrogen mission to make hydrogen manufacturing, incentivize the manufacturing and consumption also, increase the consumption. Let
Both are in, at
yes,
R&D stage only in India, you can say. Electrolyzers are costly.
fertilizer are costly.
Yeah.
That is true. But government is has
Yeah.
released fund in this budget also for R&D, and several companies are coming up with new projects in hydrogen. So let us hope what happens.
Yeah. Yeah.
So, uh, do you have any doubts in week three material, Jay?
No, no. It's
So,
okay.
so can we continue with these questions, or
Yeah,
like,
yeah.
if you have
Yeah,
any
yeah.
doubts, then we can take doubts
No,
also.
no, no.
Have
Continue. Continue as per your schedule. Continue.
it's, if anyone has doubt, then you can ask doubt. We have 15, 15 minutes. Otherwise, we can we'll continue with these questions also, and in between also you can ask. So this we have discussed. Right? So based upon discharge duration, the storage can be classified as short duration, long duration, and seasonal. So up less than 10 hours is storage. Here, different type of batteries can provide this type of discharge capability. For long duration studies, so consider this pumped hydro and compressed air, and when it these flow batteries also. Flow batteries can also provide. For more than 100 hours, chemical storage. There are some also research going on this thermal storage also, because they can also provide long discharge durations. There is one plant in Morocco. It is called Noor. Plant name, project name is this Noor. They have it has a 7 hour of discharge duration, and they use this molten salt technology. So they will use this photovoltaic concentrators. They will concentrate this solar irradiance to a point, then they heat this salt, make it in molten state, and then it can act as an energy storage. Yes, so hydrogen storage has these three main components. So first one is this production of hydrogen. So for this, we need electrolyzers. Then the second step is after producing, we have to store it. Store the excess hydrogen and then discharge it and generates electricity using fuel cells. And this we want to do, this hydrogen production we want to do using these green resources, which are these RE, the PV or wind. That is why we call it green hydrogen. So when the generation is excess, we can produce hydrogen, store it, and then when the requirement is there, generation is low, demand is more, we can use this generation from the stored hydrogen using fuel cells. So right now, what storage can do, one thing. Suppose we have this one battery storage, although it was not economical, we went for it, and we have a battery storage. And suppose this is our some daily load profile. So this is our peak load, and this is some other load. So generally, when load is during peak loads, the cost of energy is also high, and during this off-peak loads, off-peak will be this one. It's still when the suppose we can say this during this is off-peak, so here energy cost will be low. So energy cost of this is high. So what storage can do, this energy storage, it can charge itself during this time at a lower price, and then it can again discharge when the demand is high at a higher price. And the difference of these two, if it is we are able to achieve more than this installation cost of ES, then we can achieve some profit. But for that right now this gap has to be huge. It has to be some good amount. So maybe in future we can do that. Some cost can be recovered using this also. Also, we have one government has issued one guidelines on this energy storage obligation. Just now, uh, just like we have this renewable purchase obligation, we have this energy storage obligation also, where the utilities will be asked mandatorily to purchase some of their requirement from energy storage. So this is to incentivize the adoption of storage. So if energy storage obligation is comes into picture, then the storage can ask for price and they will have to pay. So in one way they can recover some of their cost, and for the rest part they can use this energy. This is called energy arbitrage. Because we are charging at a lower price and then discharging at a higher price, and the difference we are using to achieve to earn the profit. So any doubt in this? Yes, I was talking about this National Green Hydrogen Mission. So to adopt hydrogen, government has announced this one. So by 2030, we have to. This is a very ambitious target. Let's hope we can achieve this much. So for this, we need also this much capacity of electrolyzers also, and this is also in line with this renewables. So by 2030, we are also targeting to achieve 500 gigawatt of renewable. So from here you can say around 125 of gigawatt of renewable will be used for this green hydrogen production. And rest we can use for meeting our demand also. And we also plan to convert our, electrify our industrial processes and use hydrogen in industry. So government wants to incentivize the production of green hydrogen and support the domestic manufacturing. And hopefully, I think you would have heard recently. It came into my mind that recently we have found a huge reserve of lithium. I think you have heard of this. Jay, have you heard of this?
Yes, in Kashmir.
Yeah, correct.
Yes, yes.
Hopefully, the cost will reduce now within some few years.
Yes. Atmanirbhar.
Yes, correct. So we'll be self-sufficient as well as we'll be able to.
Otherwise, the cost will go rise like oil. Monopoly due to their monopolies.
Correct. So
Yes.
now we are second at position in lithium reserves.
Yes.
So that is good for us for our
Yes.
renewable target also.
Yes. It will help a lot.
Correct. So these are the targeted sector for this pilot project. So biomass to hydrogen. This is one of the main focus of this green hydrogen. So you want to electrify our heavy mobility sector also. This transport sector. I think recently the one minister Nitin Gadkari, he came up with this fuel cell based car. So these things are coming up. There is one company which also manufactures premium car, but they have one car which has a hybrid storage of this supercapacitor plus fuel cell. They use these two. So they use this supercapacitor for in this acceleration or sudden power requirement. Supercapacitor can do that. It has a high power density at very low energy density. So their fuel cell can come into picture. So they have contrary characteristics. That is why they make a good combination also. So this can provide a good power density. Hydrogen fuel cell can provide good energy density, and together they can meet the requirement of this vehicle. During acceleration, we can use supercapacitor, and then when once acceleration part is over, we can switch to this fuel cell. So they have made one autonomous car which uses this. So then third is this port and shipping, and then steel manufacturing of steel also. So in these processes, we are going to use this hydrogen as per the plan. This is I was talking about one example. This is another example where they are using hydrogen plus lithium ion. So this hybrid combination is different here. So they are using this lithium ion plus hydrogen fuel cell. But here fuel cell is not. This is not entirely a fuel cell electric vehicle. It is a hybrid of battery plus fuel cell, and fuel cell is being used as a secondary source here for the range extension. So it keeps the battery charged, and it can provide up to 500 kilometers of range for an for a truck. So benefit of this is we can use a smaller fuel cell because it is not completely a fuel cell based vehicle. So different manufacturers are this Airbus also planning to make first hydrogen powered aircraft. Then I think you would have heard of this eVTOL. Have you heard of this eVTOL, Jay?
No.
Right.
Recently, I heard some Ashok Leland has partnered with Reliance, and
Okay.
they have rolled out some vehicle. There was a news recently from Ashok Leland, and Geo
Uh,
BP has some tie-up.
is it
There
a
was.
bus, electric bus, or
No,
means
it's a transport carrier
okay.
for carrier.
It,
You can
so
Google
heavy.
and find out recently.
Okay.
Recently, it's 1 month before.
Yeah, and several state governments have also come up with these electric buses. Now we are also going for this fuel cell.
Yes.
Yes. Are you saying something?
No, electric buses are used in some public transport. I don't know whether they are running on fuel cell or pure battery. I don't know.
Right now they are running on pure battery.
Pure
But
battery.
yes, pure
So,
battery. Right now they are running on
okay.
pure battery. But in future we will see this fuel cell based heavy vehicles. In
Yes,
Ca-
yes, slowly it will come.
in Canada they have even cranes, high power cranes. They are using batteries. So they will also
They
shift.
are rich. They are rich. They can more do R&D like things, some experiments.
From there, we are also
Yeah.
we are
Yeah.
also getting something. We are also importing from even electric buses. We have imported from I think Germany or somewhere. Now we are also trying to manufacture them within our country.
Only cost will when we will start manufacturing, then only cost will come down.
That is correct. Now
Otherwise, yeah.
let us hope with the new lithium reserve we can do something.
Yes, yes. Then only turn will come. Otherwise, they are so costly.
Yes.
Good things.
So
Yeah.
this eVTOL I was talking about, no? eVTOL is a kind of a we can say e-taxi.
Okay.
Or not just taxi, it will not just be running on road, it will be flying. So it will be flying. You can say a
Okay.
drone, kind of a drone, but a bigger drone which can also carry people. So they are
Yes.
also thinking to use this batteries or hydrogen fuel cell.
Yes. Yes.
From this Airbus, I remembered this eVTOL. So
Yes.
Airbus is planning to do this. Even some shipping companies, they are also ship manufacturing companies. They are also planning to launch first ship in next year by 2024 itself.
Handling hydrogen is also a very big safety risk. Lot of
Yes,
R&D has to be done. Hydrogen was used very early in flying. You go to the history, but there
correct.
were some disasters, accidents. 100 years ago, it was started.
That is correct.
Not an electrolyzer in the other form, but not succeeded. Yes. Let us hope. Carry on. Please carry on.
Yes. Thank you for your inputs. You have given good inputs. Yeah. Let, so this is done. Let us move to the next question. So, which of the following electrochemical energy storages has the least lifespan? Lithium ion, lead acid, sodium sulfur, or flow batteries? So, what do you think? Any guesses? So, answer for this one will be this lead acid. So it has a very small life, around 3 to 6 years. You can see when in our cars we use this lead acid batteries. They are fully covered, fully packed. But if we see these UPS at homes, they have those batteries where we can even see this. We can see the water level also. We have to put this distilled water inside that when the water level goes down. Those are also these lead acid batteries. We are still using them at homes. Even the solar PV, if they have storage also, then right now we are using lead acid batteries also because lithium ion is not economical right now. But they have to be replaced within 3 to 6 years. So in automobiles generally they replace in within every 3 years they replace it. Then one I would like to tell advantage of this flow batteries. They have one advantage that because they have this tanks of electrolytes, so we can change the electrolytes, we can replace it, and we can continue using the battery. So their degradation is less in that sense. So that is why sometimes there are some. We will see. Maybe I think I have not included that. So sometimes we use this hybrid combination also. There is one Oxford Energy Hub you can search. They have this hybrid combination of batteries, these two batteries. Because lithium ion, if we do frequent charging, discharging, we have seen in the previous graph also, then its life reduces. So that frequent charging, discharging is done using this flow batteries and normal operation is performed by this lithium ion. So in that way, the combination of these two can help reduce the degradation of lithium ion. We can use it for a longer duration, longer period of time. So lead acid is the correct answer here. So this is a good question. What does the capability curve of ES energy storage describes? Operating point on IV curve, PV curve, apparent power and current curve, or PQ curve. This is a important characteristics. Just as in solar and wind we have seen characteristics, they have these capability curves. And so any guesses for this? IV, PV, SI or PQ? Which one is the correct answer?
Should be IV curve.
Okay. Uh, why do you think so?
Because maximum power tracking effect gets there.
Yeah,
The
but
combination of
Mhm.
power MPPT of phenomena can be achieved with
Mhm.
ESS operating in IV curve. That is my guess.
Okay. So you are relating it based upon that PV and wind, the MPPT, that
Yes,
tracking that we do in PV and wind. Yeah.
yes,
So okay, so I would like to just that will not actually be applicable here because why do we need that MPPT there in case of PV and wind? Because the input is changing there. It is not within our control. So whenever the input is changing, we want to just extract the maximum what we can extract from that input. But here
correct.
we have all input is almost we, this is not the case with the storage. Here input is not variable, means random in that sense. And here the storage in PV we have this IV curve like
Okay.
and this PV curve like this. So in storages, actually this capability curve is not for the source per se. It is for the that inverter. Even in this solar and PV inverters, we have these inverters have this capability curve. Even the conventional generators, they have their capability curve. So capability curve, whenever we talk about this, we always talk about P and Q. How much P and Q they can provide? What is their operating region? So this curve is like this, where this circle represents the apparent power. So because we know that P square plus Q square is S square, right? And this is the equation of circle. So in this, on this circle, we will always have this same x. But P and Q can change. They will vary. But if this is Q and this is P, and if we operate on this line, suppose these are our operating points, then this will be a constant Q operation. And if we want to operate at constant P, so what will be the line? What will be the locus? Can you tell? Just
Please
as
repeat.
this
Please
line,
repeat question.
so this line is repeat. This line represents a constant Q operation. So battery will deliver constant Q or absorb. So here it will deliver. So if you want to achieve a constant P operation, constant kilowatt operation, then where will the line fall? How will the line look like? Will it be parallel to x axis or parallel to y axis?
Look like parallel to x axis. No?
This is parallel to x
Constant.
axis, right? Q, this one.
Yes.
This is constant Q. If you want constant P, so will it still be parallel to this P axis or Q axis?
Constant P. No, parallel to vertical axis. Q
Correct,
axis.
correct. So
Parallel
this
to
will
vertical
be,
axis.
so here we have this constant P, right? Suppose this is 50, 50 kilowatt. So on this line, everywhere it's P is
Yes.
50 kilowatt, correct?
Yes.
And
Yes. Yes.
if you want a constant power factor operation, then this will be, this kind of line will be there. So these operating points will be in constant power factor, or it can be like this also.
Yes. Correct.
So, so correct option for D will be. So whenever you come across this capability curve term, so you have to think relationship between P and Q. It may be any generator, even conventional, renewable, or storage. It will always be a PQ curve for a generator, not the IV or PV curve.
Okay.
So now the next question, let us see how much we remember about the equivalent circuit that we have studied in the class, in the lectures. So this is, these are the different representation of equivalent circuit for a battery storage system. So we want to select the correct representation for one time constant equivalent circuit. So which one do you think is the correct answer? Clearly, oh, just be very clear that this is one time constant. A, B, C, D, or E. Any guesses? We can start with guesses, then we can build upon that guesses and reach up the final answer. Any vague guess will also work. No problem. Anyone? First of all, tell me once, when you hear this term one time constant, what do you deduce from it? What can you say about the type of circuit when you see this one time constant?
Should be RC circuit.
Yes. So
Inductor should not be there. Yeah.
there should be one time constant. So one time constant means there should be one RC or RL circuit. Correct?
Uh,
So that is
should be
you
one
yes, Jack. You're saying
RC. In my view, should be RC.
correct.
C.
RC is the correct RC. It should be RC, not RL. So these two
Yes.
options are not correct.
Yes.
Now we have to see whether A or C. You are saying C, correct?
Yes.
But why are you saying C? Oh, C option.
No, it's my guess. Only guess. Nothing
So,
logic.
let us build on the logic or
Yeah.
guess only. So, if we see this C circuit, what we can see here, there are two
Yes.
RC components. So, one RC means there is one time constant. The two RC components are there. That means there will be two time constant for this circuit. If these two are R1, suppose if R1 is equals to R2 and C1 is equals to C2, then both the time constant will be same. If they are different,
Yes.
then time constant will be something else. But there are
No.
these two times
Yeah.
constants. But in question, we have asked, it is asked we have to look for one time constant only.
Then A.
That means,
Clearly. Yeah.
okay, let us examine this A also. So we have reduced these two options are gone. This is also not correct because there are two time constants. We want only one time constant. So now let us examine this A option. So now are you sure A option is correct?
Doubtful because there are two resistances.
Okay. Yeah, resistance
Are
here is also in this circuit also we can say this is same, this is same, this is same. Everything is same. These three resistance are in this circuit also.
no logic.
So, what is the difference in these two circuit? There is one difference. Uh, can you see the difference?
Yeah, yeah. One is current source, one is voltage
Correct,
source.
correct. That
Yeah,
is the main difference.
yeah.
Correct. So, what do you think? This energy storage, is it a current source or a voltage source?
That's a voltage source, not
Correct.
current source.
Correct.
Generator is a current source. Any generator is a current source.
But PV is a current source.
Yeah,
So,
PV, yes.
yes. So, I think we have an exception of PV.
Yeah,
But others are all voltage source only.
yes,
So, you are correct. This should not be there. So all the four options are not correct.
yes.
Answer is this E. So this
No, no. Yes, a
correct.
very tricky question.
Yes, yes, correct. So this is the
It's a
main.
level of IIT level question, you can say.
So this was the main trick which
Yeah,
you have catched. Good. So this is the we have to see this source. So if we replace this by voltage source, right? If I replace it by a voltage source, then now this circuit is a correct circuit. So this is correct one-time constant representation of an equivalent circuit of energy storage. If you want to add one more time constant, just add one RC block here. we can keep on increasing RC blocks, but then it becomes more complicated to more computationally also challenging. It requires more computation. So studies, as per studies, we have come across that 2 is an optimal one. We can get a good representation using 2. Some of them also use one hysteresis block also here to fine tune the dynamics of this circuit.
Mhm.
So there is one book, if you want to refer, you can refer for this. Gregory, he is the author, the professor from I think which Colorado or some, I don't remember the university. He has 2 books on this, especially on this energy storage, battery energy storage. One on equivalent circuit and one on battery modeling. If you want, you can refer these 2 books. He has clear explained these things in detail. He has used this hysteresis block. So let us move to this. I think this is one of the last, maybe last question. Which of the following are not quality of a good cell balancer? So first of all, what does this? So we have seen that one of the function of this BMS is to do cell balancing. So why do we do this cell balancing?
In a set of batteries, different cell are having different voltages. So
Correct.
internal circuit current will flow, internal losses will be more over a period of time.
Hmm.
That is why balancing is required.
Correct. That is correct. So circulating currents are there, increased losses will be there. Absolute. This is correct. So we have to identify now that which of these is not a good quality of. So what should be a quality of a good cell balancer? That we want to know. So out of these 3 are good qualities. So this is obvious, right? It should be a simple circuit. We all of us.
Slow acquisition is also required. Good
Okay, high.
control simplicity is also required.
Okay. So you are
Only
saying this
high efficiency.
high.
Yes, high efficiency. In my view, high efficiency is not required.
Okay. Why high efficiency is not required?
Uh,
Uh,
it's a slow process, no? So not
uh,
it takes time.
hmm.
Slow process. Balancing is not. It will take time. So high efficiency, in my view, high efficiency is not required. It is a slow process. Equalization is a slow process.
Mhm. Let us go with the reason that you mentioned for cell balancing. Uh, just as you said that balancing is required so that we can avoid the losses, and that circulating currents those which are flowing in the circuit, right?
Yeah.
So we want to minimize those leakage currents, circulating currents, and losses. So if we want to minimize the losses, so if we minimize the losses, will efficiency reduce or increase?
Efficiency is definitely going to increase,
Correct. Correct. So,
improve.
so a good cell balancer will try to reduce the losses, so it will definitely increase the efficiency. Correct.
Okay.
Actually, actually, this is the option. Uh, Same if we take, because the losses are more, we want to quickly reduce the losses, because for the more the losses are for a longer duration, then the losses will be more. Efficiency will further reduce. Heating will be there. If losses are there for a longer duration, there will be more heating. Then there will thermal management will be under stress. There can be hotspot inside within the pack. That will create problem. thermal stresses. So we want even this equalization to be quick. So this is not the ideal characteristics of a good cell balancer. Everywhere, everything we want is simple. We want simplicity in everything. We want everything as simplified as possible because that will reduce the computation also and that will reduce cost also.
Yes, it's correct.
And we want high efficiency also and we want quickly to remove all this. Then only we'll be able to achieve high efficiency. And also we need simplicity in control also because as the complexity of control increases, again the computation increases and the cost also increases. You would see that still we are using PI controllers in most of the industrial processes. Although we have very advanced control systems, still we are using these. We are using those advanced in very critical applications only. But in most of the cases, we are using these PI controllers because of their simplicity.
Yes.
So the correct answer is slow equalization is not a good quality. I think this is the last question. So reason for cell imbalances are, I think yeah. So what are the reasons?
All should be
Correct.
self discharge, internal resistance,
This time all of the above is correct.
all.
Internal resistance difference will be there, then that leakage in circulating currents will be there, voltage difference will be there. Self discharge will also create same problem. If one cell is discharging more, then also voltage uh, imbalance in voltages will be there. Uneven temperature will also create that problem.
Yes.
It will create this thermal stress, thermal hotspots. Yeah, so first of all, let us take your input. If you have do you have any doubt in week 3 material?
The lecture notes are required. Some NPTEL courses are providing lecture notes. These are not loaded. It
And
will be
lecture notes means in sense of a compiled that
some
trans-
PDF
transcript.
forms, some transcript in some PDF form, line text form.
I think
Video
transcript is
lectures
there
are there.
in option. One option is there now on portal on the left side book.
Okay.
One option is their book. In that you will find the entire transcript, one PDF that you can check.
Okay. Let me check.
And for the slides, for all the lecture we have slides already. Slides are uploaded. I think it's there.
The slides are there.
Mhm.
For any doubt, for a pinpoint, some reference is required. That
Yeah, for that references are also given, and these doubt sessions are meant for that. You can ask your doubts in these doubt sessions because most of the whenever if in last two sessions also I saw that doubts are less, so I have prepared this slides so that we can at least discuss something. If no one is asking doubt, then 2 hours we cannot be silent. So I
and that's the correct method. You are
is it a good
following.
method?
Yeah, it's a good method. Yeah, at least communicating with the person, many things becomes clear.
That is true.
Revising things becomes more clear. It's a
So
good method. Good
So,
method.
yeah, that is true. So that is why,
Yeah,
if you have any doubt,
yeah.
you can always ask because these doubt sessions are meant for clearing your doubts only.
No, definitely. Many doubts are listening video lectures. Okay, it's concept. Your some broad concept will come, but there are so many if and buts always there.
Because those are
You have to
pre-recorded,
iterate.
we cannot stop in between and ask something. So,
That's why
yeah,
that one-to-one coaching, mentoring is required.
yes.
Otherwise, every one is of not same. potential, you can say, in terms of electrical.
That is correct.
They have different potentials level. Circulating current will start flowing between.
Good analogy. So
Yes.
that is why NPTEL has taken this initiative, and we have started. We all of us have
No,
started.
no, it's a very good, very, very good program.
So we also feel motivated when you interact
So,
so well with us. This active interaction is very important part of this problem solving sessions. So it will be a good.
mm,
If you want
that's a
to
really,
suggest any changes in the flow of these sessions, you can always do that.
no, no, it's okay. Uh, okay,
And
time is sufficient and it's okay.
I think you were asking
Carry on.
something in between. I stopped you.
Mainly, my question is related to safety aspects of hydrogen handling.
Hmm.
Hydrogen handling is a problem. It's a
Hmm.
very, uh, you can say, uh, unsafe gas to handle, store, and a lot of challenges required. Electrolyzer, okay, will technology will come, or Indian conditions are worse, you can say. So,
Yeah, that is a very big challenge. Safety issues
yes,
with hydrogen is a even when lithium ion was being developed, even lithium is a reactive element. So
yes, it's a
that
very light element.
also, yeah, even with that also safety issues were there. But with technology, with advancement technology, we have come a long way. Similarly with nuclear also, uh, nuclear is not a safe technology. You can say it has so many challenges. How to minimize the radiation, how to control them. We are using these several techniques we are using to minimize the radiation. Still, some there have been some disasters in past, and still something may go wrong. Handling nuclear also we have to handle it with a great care.
Yes, yes.
So maybe yes, for hydrogen we certainly we have to work on the safety issues that we have to do.
At least in vehicle, our petrol tank is below the vehicle.
That
At
is,
least something happen, all will spread on the road and we can escape.
but hopefully uh, will not have petrol in those cars.
So handling, storage,
That
is a really an issue
even
right
transportation
now.
also.
Yes, transportation is also issue.
So I think we're going to we'll have to work on that. Certainly we will have to work.
Yes, yes.
So any other doubt? Yeah.
No, it's okay. Any R&D work is going on in IITs or hydrogen field? Any partnership with other companies like Europeans?
For hydrogen,
Development of technologies?
particularly I can't say, but certainly work is going on in hydrogen. Even in carbon capture, hydrogen, all these new technologies are being explored in IITs. But for specific details that I am not sure about those details. Because they generally material they that research is from material point of view, materials, material engineering and design perspective. So we have to ask the other departments for that.
Okay.
Energy science department is working in that. Maybe
Okay.
next time if I interact with them I can ask them what kind of research is going in that direction, and I will let you know.
Yes. Material science of field of many IITs are doing that. What Bombay is doing,
Hmm.
I think Guwahati is also doing material sciences. What, yeah, lot of things are going on.
Yes.
Yeah. But
So
hydrogen, to make it economically viable, a lot of effort is required from our
next,
academic institutions also.
yes.
Industries will only put their money when they are see some profit.
Yes.
Otherwise, they are not going to put
I
there.
think industries there
Yeah.
several industries are planning because they are saying government is also providing so much budget and future is actually so we need hydrogen in future. We have requirement for that. We want to electrify our industrial processes. We want to electrify our transportation. We want seasonal storages. All these hydrogen is a good candidate. So
But
that is why several
incubation
countries
should,
are also working on that.
but incubation is required in our academic institutions, top level academic institutions.
That is true.
Industries, I'm related, I'm from my industry, I know. No
Hmm.
industry is going to put, they will commit so and thing unless they got chunk of money as a PLI from that.
That is
But
true.
initially,
Only
we have to invest for that. We have to invest for that.
yes, yes. You are correct.
Yes. That is, so my why question was that any government initiative is being taken place here or IIT's premier institutes
I
where
think
some technology work is going on there.
because
So,
recently this National Green Hydrogen Mission they have announced in this budget also. So
yeah.
they are financing some projects in IITs also. So IITs will be taking up new projects in this hydrogen production also. How to reduce the cost of hydrogen production? IITs are certainly going to work on that, and government is going to fund those projects. So
Yes. Yes.
within next year, 1 or 2 years, we can see good number of projects on hydrogen.
Yes. Correct.
So I have one last question for you.
Yeah. Yeah.
Would you like to answer this? So,
Yeah.
so question you can see on the screen. Why linearize the power flow equation for optimization?
Linearize.
So this is the last slide.
So forget this part.
No problem. We can discuss. Will it be okay? I will just take 2 minutes.
No. 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 Time is not a problem for me as far as you are free. Oh,
Yeah.
we can discuss.
Thank you. I
So
would just like to thank you for such an active participation.
yeah.
It is always good when one is discussing. It's encouraging for us also.
No.
So
No. It's a two-way traffic.
correct. So
Linearization means, in my just a wild guess, power flow to have a smooth uh, power flow. It's a required. It's a requirement. You can say. So,
okay,
efficiency.
so I will just tell that.
Power flow voltage and currents.
Hmm,
Power factor should be less. It's a requirement. You can say of the
actually,
power transmission distribution.
you're correct, but actually, this question is more from a mathematical point of view, computational point of view.
Okay,
Uh,
that's
when
I'm not remembering equation, so
no
I'm
problem.
not in a position to talk more on this. Yeah.
So actually, if we see the very simple equation, this is a very simple equation. If we have this one generator here, one line, one load here, this is voltage. This angle is E angle delta. This is V angle zero. X is the line reactance. Then this will be the P. Similarly, we can write Q also. So here we
Yeah.
can see this P is related to delta. So this is a non-linear equation because of the sine term.
Yes.
Sine is a non-linear function, correct?
Yes.
If this had been this EV by X delta, then it would have been a linear function. And
Yes.
dealing with these non-linearities in optimization is a very difficult cumbersome process. It's very problematic because first of all they will increase the competition. We need to use different techniques, and other thing is that we are not sure whether suppose this is a function, this is some function that we want to minimize or maximize.
Yes.
and we are somewhere here. So our techniques will say that this is minimum in this neighborhood,
Yes.
but actual minima is this one, not this one.
Okay.
In vicinity of this point, this is a minimum. That is true. So we call it a local minima. But actual
Okay.
minima, this is the global minima. So this is a
Yeah.
problem with these nonlinear functions. They have multiple local maxima and minima, and to track this local minima is very challenging. So we always try to linearize these functions, these equation, our objective function, our constraints. We want to linearize them as much as possible. So that is the main reason, and also because a linear function is a convex function. Have you heard of this term?
Yeah. Yeah. That I know.
Correct. So because the speciality of convexity is that we know that a convex function will be something like this,
Yes.
and we
Yeah.
will certainly, if we reach this, we can certainly say that this is the global minima. We don't have to worry that
Yeah.
whether
Yeah.
it's local or global. It will always be a global minima.
Yes.
So that is the beauty of linearizing these power flow equations. So we get convex equation and convex optimization. We have good solvers available for convex optimization, and we can get our global minima or maxima. That is why
Yes.
in that question of optimal, in that lecture of optimal sizing and sighting, we have linearized the power flow equation.
Okay. Okay. Right.
Okay, so now I think it's over. These are the references. If you want, you can go through them. That I have used these references.
So this slide will also be loaded, huh?
Yes, I will
Already.
upload it right now. I will upload it in the problem solving. That link you can get when Google Drive is available. In that you will find this slide. But
Okay.
video, recorded video, I'll be able to upload tomorrow only. It will take
No
time.
problem. No. No.
Slide I
No
will
problem.
upload right now only.
Okay.
Okay,
Good.
so let us conclude then.
Yeah. Yeah. Thank you very much. It was a very good session.
Thank you
Very
for
good
your
session.
active participation. I hope to see you again in the next sessions also.
No. No. I'll definitely join this.
Thank you once again.
Join. Yeah. Join little bit late, but it's very useful for me. You can say. Thanks.
Thank you.
Okay. Yeah. We'll sign off. Yeah.
Yeah,
Now.
sure.